Almost every location in the universe is at almost the same temperature, just over 2.7 Kelvin, the temperature of the microwave background. And we can explain why that is. And we can explain why some exceptional locations, like this one, are warmer. It's because some other exceptional locations over there are much warmer still. So if you were asked to explain how anything can exceed a temperature 10 to the 7 times that of, say, the background, the microwave background, 2.7 Kelvin, then you'd probably think of something like the centers of certain stars. And in that case, your explanation would be in terms of nuclear reactions and gravity and stellar hydrodynamics. And if you wanted more detail in your explanation, you'd also want to include theories of stellar evolution. And if you wanted to set your explanation in its broadest context, then you'd also want to include theories of star formation and galaxy formation and ultimately the initial conditions at the Big Bang. And throughout your explanation of all this, your mode of explanation would remain the same. Basically, you'd be using universal laws of motion to predict that the various phenomena that you're explaining, and ultimately the high temperatures, are inevitable given the initial conditions, ultimately at the Big Bang. I'll call that mode of explanation by prediction. And it's typically appropriate for phenomena that happen spontaneously, like stars. But now imagine that you were asked instead to explain how something could be cooled to a temperature below 10 to the minus 7 Kelvin, or 10 to the minus 7 of the background, shall we say, to make it invariant. Well, now you'll require an explanation of a wholly different character. I mean, for a start, explanation by prediction is now totally intractable. Temperatures so low are only ever achieved artificially, and nobody knows how to apply equations of motion to the initial conditions at the Big Bang and work out the probability that, or even more recently, a century ago, and work out the probability that there will one day be low-temperature physicists who will invent refrigeration by laser cooling. Predictions like that are only possible in fiction. But in any case, even if that were possible, it wouldn't be good enough. Because how something can get that cold is really not, it's much less a matter of the laws of motion of the thing being cooled, as it is a matter of how the thing doing the cooling works. And that mode of explanation, how the thing works, is, just to jump ahead a bit, that would be what I call explanation via constructor theory instead of by prediction. The refrigerator is a constructor. And roughly speaking, I'll be more precise in a moment, a constructor is anything that can cause a transformation of a physical system. And I'll call the systems that it transforms its substrates. So a robot on an assembly line is a constructor, and its substrates include components which it transforms from an unassembled state to their assembled state. Now, obviously, the combined system of the refrigerator and its contents and its power supply and everything else that's needed do evolve spontaneously. So, and they evolve under the same universal laws of physics as stars and physicists and everything else. So, why exactly do those low temperatures require a different mode of explanation from the high temperatures? Well, take a cloud of gas that's going to collapse to form a star and alter it. Don't add or subtract anything, but just move the bits of it around, shuffle them like a pack of cards. Then step back, or move back in your spaceship, and wait. Well, it'll still form a star, and it'll still get hot, and your explanation of why will still be true. And so, because the phenomenon you're trying to explain isn't dependent on the fine details of the initial conditions, you don't have to explain those initial conditions in order to explain the phenomenon. And actually, the same is true of the sliver of material that's being cooled by the ultra refrigerator. But it's not true of the refrigerator itself. If you shuffle its bits around, then it'll no longer work. And so your explanation will then no longer be relevant to explaining what it does. So that's why, in this case, you have to explain what it is about the initial conditions, the condition of being a refrigerator, that makes it able to cause cooling. Even though the slight variant of it with very similar initial conditions and obeying exactly the same laws of motion is not capable of that. Now, actually, the overwhelming majority of phenomena that can possibly happen under the laws of physics can only happen if some constructor causes them to. But at present, there's no fundamental theory of that. The situation is very like what computing was before Turing or before Babbage. There were plenty of theories about computations and particular computations, but there was no unified theory of computation. And it took even longer once we had one, to incorporate that theory into physics as it is now. And similarly, today, we have lots of theories about constructions and about constructors, but there's no constructor theory. What we have is little bits and pieces of it that have been set up ad hoc, pragmatically, to solve particular problems, to explain particular phenomena, and so on. And in fact, constructor theory itself was first mooted entirely pragmatically by John von Neumann in the 1940s as an exploration not of theoretical physics, but of theoretical biology. He wanted to understand how it is possible for a physical object, like an organism, to reproduce itself and to evolve ever more complex adaptations for doing so. And this is old hat today, but von Neumann was working before the discovery of DNA. Today we know exactly how it works, but he was interested in the problem of principle. And his approach was to set up a model physics with simple objects with simple interactions with each other, and he hoped to use this to set up a model biology in which there would be model organisms that reproduced themselves and evolved. And when that didn't work, he simplified it all even further and thereby inadvertently invented what we today call cellular automaton theory. With the benefit of hindsight, this artificial physics approach was a bad idea. It was still trying to use the wrong mode of explanation. You can't understand the life cycle of an organism by writing down its equation of motion. Nevertheless, von Neumann managed to solve the problem anyway, not by using his model, but by what I would today call informal constructor-theoretic reasoning. And so he realized that what you need to make a self-reproducing, evolving constructor is that it has to operate in two phases. First, copying its, it has to be a programmable constructor, and first it has to copy its program, and then it has to execute that program, to build another instance of itself. So that was the first triumph of constructor theory, if you like, but it was a dead end, because by retreating to the theory of cellular automata, von Neumann totally missed the most important thing about constructor theory, which is that it is a branch of physics, and in fact, the most fundamental branch, as I will explain. Now, right away, you may be wondering how constructor theory can possibly be fundamental in any way, because constructors are composite macroscopic objects like robots, factories, living cells. So how can the theory of them possibly be physics, let alone fundamental physics? Why isn't it engineering or robotics or something? Well, hold that thought. That's the right thought to have. I'll come to the general answer in a moment, but first, just consider a fundamental area of physics where what I'm calling constructor theory was traditionally applied already, namely classical thermodynamics. Heat engines are constructors, and their classic substrates are a hot body and a cold body and something else like a piston. And the transformation they cause is to cool the hot body and heat the cold body and thereby typically do some work on the piston. And also, the laws of thermodynamics could be expressed as statements that certain classes of construction task are impossible, such as constructing a perpetual motion machine of the first kind, of the second kind. So, those were fundamental laws of physics expressed in constructor-theoretic terms, not as equations of motion and initial conditions, an explanation by prediction, but constructor-theoretic terms proper. Hold that thought as well. Okay, now, it's essential to the definition of a heat engine or a purported perpetual motion machine that it be capable of operating in a cycle. That means that when it's done its thing, it's just as capable of doing the same thing again to another instance of the substrate. Why is that essential? Because if it isn't capable of doing that, then when it acts, it is depleting some resource. And therefore, its effect on its ostensible substrates isn't a complete accounting of what it does. And to get a complete accounting, we have to include the depleted resource as another substrate. And for exactly that reason, I will define a constructor in general, now here comes the exact definition, as anything that can transform a physical system while itself undergoing no net change in its ability to do so. And also, for the same reason, we have to think of the constructor and its substrates jointly as being an isolated system. This doesn't exclude any possible constructions, because we can always regard part of the environment as another substrate if it's interacting. Okay, so another familiar example of a catalyst satisfying that definition is, I gave it away, of a constructor is a catalyst, a chemical catalyst. It transforms chemicals into other chemicals, while itself remaining chemically unchanged. Well, not literally unchanged, because catalysts can get poisoned, they can undergo other interactions. Constructors in general wear out, they require maintenance. So there's always an issue of error correction, which I will totally ignore in this talk, because I'm expecting that, just like in the theory of computation, quantum computation, it will turn out that error correction makes no fundamental difference to the theory, even though it's necessary in every computation, and in this case, construction. So, this chemical equation describes a construction. It's the Haber process for synthesizing ammonia. There's the catalyst, which is the constructor. There's the initial state of the substrate, and there is the state it gets transformed to. The delta represents energy production because it's exothermic. Now, this is a key point. Let me abstract away the constructor from this description. That is just a specification of a transformation, not how to cause it or what causes it. And I call that a construction task. And that is actually what constructor theory is all about, not the constructors directly. In fact, this is a possible construction task. That means that some constructor would be capable of performing it. There are also impossible construction tasks, like this one. With a 3. That's impossible because of the laws of chemistry or the laws of conservation of baryon number or whatever, but laws of nature. And this one is another, with the minus sign, is impossible because of the law of energy conservation. Now, in practice, a catalyst usually has to be part of a much bigger constructor. In the case of the Haber process, it's something like that, which I downloaded from the internet. As I said, constructors are composite, complex, macroscopic objects. But the task that performs is simple. It just takes all that machinery to ensure that that simple transformation is in fact what happens. And that is also the key to how constructor theory can be fundamental. We can make it not the theory of construction processes or constructors, but the theory of possible and impossible construction tasks. How to build constructors is then derivative from that theory of tasks. And it isn't part of fundamental constructor theory, though it follows from it. So now, let me sketch what it might look like to reformulate the whole of physics in terms of construction tasks instead of initial states, laws of motion, as at present. I better stress right away that there's nothing anthropocentric about this project of looking at everything in terms of tasks. Constructor theory is about what can or cannot be caused, whether it's caused by a molecule or a factory or a physicist. Actually, I'll begin in a way that's slightly contrary to the spirit of constructor theory, but we really have no choice at present. Namely, I'll give an exact definition of construction of construction task in terms of states and their evolution. Now, once there's a fully developed constructor theory, it'll be the other way around. States and laws of motion will be expressed in terms of construction tasks, perhaps only as limiting cases. So this definition that I'm going to suggest is only for the sake of illustration and motivation. I won't use it in the theory itself. Anyway, in that spirit, the definition is: a construction task is a set of ordered pairs of states of some substrate. Each ordered pair consists of an input state for the construction and one of the output states that shall count as having performed that construction on that particular input. So a given value of x can occur more than once in that list, each with a different value of y. And I'll say that a constructor is capable of performing that task if, whenever it's presented with the substrate in one of the states x, it transforms it to one of the states y that's in an ordered pair with that particular x. Now, I'll call a task possible if a constructor capable of performing it is possible. In other words, if the task of constructing such a constructor is possible. So that's a recursive definition of possible task, which the root of which must therefore be naturally occurring objects. That's objects whose creation can be achieved by the null constructor, that is, doing nothing. Okay, now we can try to leave behind states and laws of motion and all their associated conceptual framework and try to think entirely in terms of possible and impossible construction tasks. The serial composition, AB, of two tasks is the task. Now, this is not quite what you think it's going to be. It's the task of achieving the net effect of performing B and then immediately performing A on the same substrate. This notation is obviously borrowed from the theory of computation and related theories, but note that those boxes represent construction tasks, not constructors and not constructions. Therefore, performing AB need not involve performing either A or B. AB may be a possible task even if both A and B are impossible. And that's actually the interesting case, as we'll see. So next, there's the transpose of a task. Now, I'll actually motivate this with a bit of a sneak peek at the definition of tasks in terms of states. It's just a motivation. In these terms, the transpose A twiddle of a task is just A with all its pairs of states reversed. But in intrinsic constructor theoretic terms, the transpose is just defined like this. For every task, there exists a task with the following properties. The transpose of the transpose is the original task, and performing the transpose leaves a substrate that's suitable for the transpose of the transpose, and vice versa. And A twiddle A and A twiddle can be performed by the null constructor, among other things, possibly. It follows that if a task viewed as a relation is a one-to-one relation, then its transpose is its inverse. That is to say, A twiddle A or A twiddle has the same effect as doing nothing, which is the null constructor or performing the unit task, which I call I. Okay, now the parallel composition, A cross B. That's the task of achieving the net effect of performing A on one substrate and B on another. Again, without necessarily performing either A or B individually. And similarly, any network of construction tasks is a construction task. may or may not be possible, but it's a construction task. Which brings us to a purely constructor-theoretic law of physics. Namely, that even though a network of construction tasks just specifies an overall effect and doesn't say anything about how it can be done or whether it can be done, nevertheless, any finite network of possible tasks is a possible task. I call that the composition law. And note, for example, that physically conveying a substrate from the output of one construction to the input of another, as that would be if those were constructions, is itself a task and is in general not a possible task. So this is a non-trivial statement, this composition law. It's a proposed law of physics. Okay, now I'll define a certain relation between tasks, symbolized like that. Its physical meaning, its intuitive meaning, is roughly that A and B, if they are impossible for the same reason. So I'll call this in words, A is like B. And its formal definition is that both A twiddle cross B and A cross B twiddle are possible. It's an equivalence relation. Trivially, it's symmetric. The definition is symmetric. And it's reflexive because of the properties of twiddle. Basically, A twiddle cross A can be performed simply by swapping the two input substrates, and that is possible because of the composition law. But it's transitive for a much nicer reason. Okay, suppose that A is like B and B is like C. Then, by the definition, the four tasks A twiddle cross B, A cross B twiddle, B twiddle cross C, B cross C twiddle are all possible. And therefore, so is that task, 1 cross B twiddle cross C, composed with A twiddle cross B cross I, by the, I said 1, I meant I, by the composition law. But that task is the same as this task, and there, the second substrate is undergoing B twiddle B, which is possible because one can perform it by doing nothing, which guarantees that the second substrate could be reused. And therefore, the second substrate could be reinterpreted as being part of a constructor that performs the task A twiddle cross C on the first and third substrate. So A twiddle cross C is possible. By the same method, we can prove that A cross C twiddle is possible, and therefore that A is like C, which completes the proof that is like is an equivalence relation. By the way, if anyone can think of a nicer name for it, then please let me know. Okay, so it's an equivalence relation, and therefore it partitions the set of all tasks, the class of all tasks, into equivalence classes. So let's consider those equivalence classes. For a start, exactly one equivalence class contains the unit task. Each member, because of the definition, you can see that each member of that class, of that equivalence class, must be possible, and so must its transpose. And therefore, that is the least interesting of the equivalence classes, because the real content of any scientific theory is in what it forbids. So, now consider two tasks A and B, which are from the same equivalence class that does not contain the unit task. Then, at least one of A and A twiddle is impossible, and the same for B and B twiddle. It also follows, under that assumption that it's in an equivalence class that doesn't contain the unit construction and unit task, It also follows that if A is possible, so is B, and that follows by considering that task. And again, reinterpreting the first substrate now as being part of a constructor. And the same for A twiddle and B twiddle. So that doesn't actually leave many cases. Either A and B are possible, but neither of their transposes is, or both are impossible and their transposes are possible, or neither they nor their transposes are possible. They're all impossible. And the latter is the simplest and most interesting case, so I'll just look at that. Because just think what it means. The transpose of A can be achieved if it's done together with B. And the transpose of B can be achieved if it's done together with A. But none of those four tasks individually is possible. Now, why would that be so? Well, one possible explanation would be that they're all forbidden by the same conservation law. For example, if A and B both call upon the constructor to increase the energy of the substrate by the same amount, then A twiddle and B twiddle necessarily call upon the constructor to decrease it by that same amount. But things like A cross B twiddle and AB twiddle wouldn't change the energy, and that might allow them to be possible tasks. It wouldn't require them to be possible. In fact, nothing I've said so far requires any task to be possible, except the unit task, which has to be possible by the composition law. But there are fundamental principles of nature already known which do imply that certain tasks must be possible. One of them is the principle of testability. Usually it's considered just a methodological rule that we only accept testable theories in science. But that does imply that for every knowable law of nature, the task of constructing an apparatus to test it is a possible task. In fact, if we follow through the logic of that, we have to conclude that possible tasks are absolutely legion. But on the other hand, not all tasks can be possible, because if they were, science couldn't possibly say anything. And that's also why constructor theory is the whole of physics. In fact, it's the whole of science, because if you had a theory that partitioned the class of all tasks into possible and impossible and explained why, then you would have expressed all true explanations of the natural world, and that is science. Okay, now, if a conservation law really is the explanation for some of those equivalence classes not containing the identity, then we might expect there to be a parametrized set of equivalence classes, one equivalence class for every value of, say, the energy by which that class, by which the construction task requires the law of conservation of energy to be violated. And we'd also expect things like pairs of possible tasks that increase the energy by E1 and E2, and another task that decreased it by that changed it by minus E1, minus E2, such that none of those are possible, but all three of them together are possible. The composition of all of them is possible. And we'd also expect there to be some two-parameter families of equivalence classes under is-like, corresponding to each one corresponding to an impossible task that violates two independent conservation laws. And that's what conservation laws look like in constructor theory. Okay, now consider a set of tasks T lambda parameterized by the elements lambda of a group in such a way that the logic of the tasks mirrors the algebra of the group. T lambda T mu equals T of lambda star mu, where star is the group operation. Then, by the conservation law, T lambda star mu is possible whenever T lambda and T mu are both possible. And then also, T lambda inverse, the T lambda twiddle is T lambda inverse, which is also T lambda inverse. And if such relations exist among tasks, then in the old language, that indicates the existence of transformations of physical states of some substrate. And so if, furthermore, that set of tasks has the property that for all tasks A and for all members lambda of the group, T lambda inverse A T lambda is possible whenever A is, then the group corresponds to a symmetry in nature, because if all distinctions between possible and impossible tasks are invariant under that group of transformations, then all laws of physics must be too. So, conservation laws and symmetry groups are naturally expressed in the constructor-theoretic conception of physics. In initial conditions are only slightly less fundamental. They are about which constructions can be performed by the null constructor, i.e. what's already there at the outset. But laws of motion, in the constructor-theoretic view, are derivative truths. They are, and may be, approximate. Who knows? They are about constructions whose substrates include clocks, and maybe rods, and so on. Now, once we give ourselves permission not to shoehorn all fundamental knowledge of physics into the pattern of states and laws of motion and explanation by prediction, we can see that actually several aspects of existing physics are already constructor-theoretic now. I've mentioned constructor-theoretic thermodynamics, classical thermodynamics, but even today, the second law is notorious for having no exact statement in the existing formalism. Why? Well, it requires there to be irreversible processes. And irreversible processes are forbidden by the laws of motion. So, okay, we say, well, no, it's only macroscopic objects that obey the second law. But at some level of coarse graining. But the distinction between microscopic and macroscopic and between coarse-grained and fine-grained is arbitrary and inherently approximate. But a law of nature can't be inherently approximate and can't contain arbitrary numbers. So could it be that there is an exact law there, but it's neither only microscopic nor only macroscopic, but wholly constructor-theoretic? And it would be something like, building a perpetual motion machine of the second kind is an impossible task, even if there are only a few atoms involved. Now, such constructions on atomic scales are liable to be quantum mechanical, and the constructor theory that I've sketched already accommodates quantum mechanical constructions very naturally. For a start, they're all related by unitary groups, and the important distinction between coherent and incoherent tasks can be easily stated. Basically, coherent tasks can be composed in certain ways that incoherent ones can't. And so if quantum constructor theory pans out in the way that I expect, then an immediate dividend might be that it would clear up an issue at the foundations of quantum theory that's already thought to be related to the second law problem, namely the definition of a decoherent task is likewise approximative and somewhat arbitrary. So, but a decoherent task can be defined exactly. So it'll be something like a serial composition of tasks, each of which can be tested during a test of the overall task. That's a decoherent task. The theory of computation is the branch of constructor theory where one regards all substrates purely as information-carrying media and ignores all their other physical properties. So constructor theory, conversely, is the ultimate generalization of the theory of computation, fully unifying it with the rest of physics. But there's also another unification that's interesting that links computation and information on the one hand with physics on the other. Namely, information, by my definition, can be an abstract constructor. For example, the ideas that I'm trying to convey to you now, and which I hope will affect your physical behavior in the future, were instantiated in quite diverse physical forms on their way to you. Patterns of electrical activity in neurons, and magnetic and electrical and quantum mechanical phenomena in computers, and sound waves in the air, and mechanical vibrations in your ears, and so on. And the explanation for the causal properties of that entire physical process is not in the specific laws of motion of the objects concerned, but in their abstract content, the meaning of the information. And moreover, it's only that meaning that remains unchanged and able to cause the same transformation again, not any particular physical instantiation of it. So it's only the information that satisfies the definition of a constructor. Abstract constructors also appear in the constructor-theoretic version of the theories of measurement and preparation. Just look at the upper diagram there. For computations, the inputs and outputs are both abstractions. Measurements are constructions whose inputs are physical objects, but the outputs are abstract descriptions of some aspect of the object. And preparation is the other way around, or preparation is also programmable construction. It's where an abstract definition causes a constructor to construct an object meeting that definition or specification. And then there are the purely material constructions. Von Neumann's constructor theory also led him to one further useful idea, the famous one, that of the universal constructor, one that can be programmed to perform any construction that can be performed. And this idea has been discussed ever since, but much more in science fiction than in science. But I believe that the laws of constructor theory, I haven't described them all today, imply that a universal constructor can be constructed. And that raises all sorts of other interesting issues. For a start, it strongly suggests that we are already universal constructors. And also there must be a smallest universal constructor. How small? Is it nanotechnology, or is it some factory or planet? In any case, it would have to be a universal quantum constructor. And as Simon Benjamin has pointed out to me, there is no such thing as a universal classical constructor. This is another unification, because say we were universal classical constructors, we'd be able to construct a universal quantum constructor. Well, who else is going to? And therefore, we already are one, even though we are decoherent systems. And also, within computer science, there's yet another unification implicit in constructor theory. It unifies two of its branches. One is the theory of computability, what can or cannot be computed, which is the analog of constructor theory as I've defined it. And the other is complexity theory, which is the theory of the resources, such as time and memory capacity, that are needed to compute functions that are computable. So, is there a constructor complexity theory, analogously, that studies the resources needed to perform constructions? Of course, there is not. And here's why. Consider a parameterized set of tasks with two parameters. The task is to transform a mass m of hydrogen, that m is the first parameter, and an available energy E, that's the second parameter, into 1 kilogram of gold, plus possibly waste products. For some values of m and E, that's a possible task, and for others, impossible. So we can illustrate that in a diagram like this. Gray shading means possible task, and white means impossible. And there at the bottom left is the limit imposed by conservation of energy and E equals mc squared. But in fact, one couldn't achieve that for smallish amounts of matter and energy. So the actual boundary would be above that, say it's the heavy line. But now look, that same line is also a graph of the resource requirement for another task, namely performing the transmutation on an input just of mass m using some resources. And this is unlike in the theory of computation. So there's the unification. And note also that, as this illustrates, in constructor theory, it's meaningful to ask what the complexity of a task is for finite values of the input. Now, the fact that this isn't even meaningful in existing complexity theory ought to be embarrassing for that theory. I don't know whether it is considered embarrassing, but it's inevitable until complexity theory is brought explicitly into physics. And that can only be done via a constructor theory. The theory that I've presented here, though, is more of a demonstration that it's possible than it is a fully fledged theory. Any of the specific laws or ideas that I have suggested could be false. For instance, the composition law could be false, in which case it would be really interesting to know not only what the specific exceptions are, but what the actual truth of the matter is in general. Because, as I said, constructor theory promises all these various unifications of laws of motion with thermodynamics and decoherence and macroscopic with microscopic and abstract constructors with concrete ones, and bits of philosophy like the principle of testability with physical laws. And I've just mentioned computability and complexity theory and so on. And the thing is, all these unifications have to happen eventually. We're just habituated to the lack of them. But that is just a signal of the fact that there are gaps and inherent vagueness in the current conceptual framework of physics. So there must be such a unification, whether it's just like I've envisaged or not. So I'm not saying that there are some loose ends in this theory. I'm saying it consists almost entirely of loose ends, but nevertheless, or rather, therefore, I commend it to your attention. And thank you very much for listening.